Okay, we're back. This is 9.4. We're looking at exponential growth and decay. We talked about growth and decay a little bit on the other ones when you can determine whether it's growth or decay by looking at the base. If the base of the exponential function is a number bigger than 1, it's exponential growth. If it's less than 1, it's exponential decay. So populations grow exponentially. And well, sort of. It might actually be logistic where it looks like this. It looks exponential, but a lot of times it'll plane off to a carrying capacity. But they're talking about people, population of people, and so it's exponential. We haven't hit that carrying capacity yet. It might be there, but most animals, when the food supply starts running lower, they stop procreating, and so you get this carrying capacity where there won't be more than those numbers. All right, that's why they're always worried about people bringing animals into an environment where there's no natural predators, and because a lot of times they'll take over because nothing will eat them. All right, so let's take a look at number 2. In 95, let's suppose a town named Jackson had a population of 15,500, was consistently increasing 10% per year. If this yearly increase continues, predict the population in 2015. Okay, so it was 1995 to 2015. So we're looking at 20 years. So that's going to be our X is going to be time in years. We have an initial amount, C, that's the 15,500. 1 plus the rate, a 10% growth rate. That's a real healthy growth rate. But remember, in order to play with the real numbers, we got to make it a decimal. So 0.10, 2 places to the left, or divide by 100 if you like, and then to the 20th power. So now we do order of operations. We parentheses 1.1. And then to the 20th, 15,500. Then we do exponents, so that works out to be, let's see what that works out to be. 15,500 times what is, clear 1.1 to the 20th is 6.727499949. All right, and we multiply that by 15,500, and so we're looking at 104,276.249, but we'll just call it 6 people. We'll round to the nearest whole number. So it went from 15,000 in 20 years to 104,000. That's quite a growth rate. All right. Okay. So let's look at exponential decay. A large golf country club holds a tournament that is single elimination. That means as soon as you lose, you're out. And it starts with 512 people. So after 6 rounds, how many people are left? So each time, half get removed. So here's our equation. Oops, that's an R. To the X. So we had 512 people to start. This one's for exponential decay. That would be decay. 50%. Every time somebody plays a matchup, one of them gets eliminated. One of them gets to stay. And so they want to know, what does it look like after 6 rounds? So we do 0.5 to the 6th power, and then times 512. That's 0.015625. That doesn't go on infinitely. That stops. So after 6 rounds, we're down to just 8 players. And so if you've watched like the World Poker Tour thing ever, they have sometimes like 10,000 people, And they get it dwindled down pretty fast with in just a couple of rounds. You know, it isn't like what you would think. A lot of people are like, oh my God, they must have played 20 rounds or 30 rounds. No, it's pretty fast. So 512 people, 6 rounds of golf. We're down to 8. All right. Okay. So then the next one they did for us, page 15, that's the half-life of stuff. So 72 years, 15-year half-life. That means it takes 15 years for half of it to decay. That's the chemicals, the DEET. DEET is really good to keep the mosquitoes from sucking your blood out of you, but it's really rough on the environment. So I know in Vietnam they were dumping that all over the place. So that's a half-life problem, and so they did the 4.8 years, and after 72 years, what do they have? From the table, we see after 72 years, between 4 and 5 intervals, there should be between 12.5 and 25 pounds of DEET remaining, the DDT. So, in 72 years, 14 pounds still remain of the original amount. That's a lot. Okay, so that one was done for us, though. All right, then the next video will be on log functions.